Ooh. Hey everybody, this is Larry. This is day 12 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's poem. 1095, Finding Mountain Away. Alright, we have a hard poem, should be fun. I'm really tired. I've been on the plane or some form of traveling for 25 hours. I got some sleep, but not quality sleep. And every time I get some problem about mountains, I usually would put in like a drawing thing, but today I am too tired to do that. So let's see. I am even going to finish doing this problem really quickly as early as I can. So let's do that together. All right, 1095. Find in mountain away. So away is a mountain away if it's more than three elements. It's okay. So it goes right. Given a mountain away. So it goes all the way to the front and the end. Okay. So given a mountain away, turn minimum index such that mount. Okay, so we know that this is a mountain away, and we're trying to find target. If such an index does not exist, we turn -1. You cannot access it. You can only either get n or length. Okay. So assume that we always get this for free. What's it called? Mountain dot length, right? So we get this. And I assume that, okay, yeah, you only make 100 calls to get. So, I mean, it's very obvious that they want you to do some sort of binary search, and it's 10 to the fourth. So we have to figure out how to do binary search, right? That's a little bit of cheating, though. But we can think about it. Let's see. So we're just trying to find some target, right? Mm, let's see. So this is a mountain away. We have to return. If there are more than one, we have to return the smaller one. Okay. Mm, I mean, the thing with binary search is that there's a loop invariant that we basically has to try to do in general, right? So that you can kind of bisect it every time. You also maybe do a ternary search, maybe. Um, hmm. Okay. I think one thing that I was thinking about in an edge case kind of thing, but it actually is not happening, is that all the numbers should, well, it's not unique, but adjacent numbers will not be the same, right? So that means that a target can only appear twice, once on the upslope and once on the downslope. And and given that we have to find a minimum index, we're trying to find the one on the on the upslope side first, and then if it doesn't exist, do on the downslope side. I think that should be good enough. Um, hmm. I think for these problems, it's important to kind of just figure out, you know, I mean, given 100 cores, that's way enough time to do anything. Because even if you do 3 cores to get one bit of information, that's going to be 2 to the 33, which is more than enough for 10 to the 9. Um, but I think we are going to try to. There are a couple of. I think I'm just like a little bit. I wouldn't say stuck, but just thinking about what I want to do. There are a couple of ways you can attack it. One is to just kind of find a peak and then kind of bisect on the peak after that. I don't know if that's too slow or not. That's why I'm kind of struggling a bit. And then the other side is just I don't know, just like kind of play around with just binary search in general. Um, yeah, you get the first element and then you just kind of take the middle element and then does that tell you anything? I guess technically not because it can appear on both sides of a mountain, right? I guess that's a little bit of a yucky part. Am I? Oh, is my head too big? I don't even know. Um, Yeah, let's think about this. I'm just trying to think whether. So I think I can do the find the peak part, and then from that just find it from the left side and find on the right side. That should be pretty straightforward. I'm just kind of wondering if that's too slow. So we can find the peak in, let's see, 10 to the 4th, and we do 2 cores each. Okay. If we do 2 cores each, then after what's 10 to the 4th? 10 to the 4th is 10,000. So that's what, like 15, 14. So times 2 is 28. So we make 28 cores to just get the peak, and then we do a binary search on the left. That should be at most 14 cores, and then another 40. I guess that should be okay. It's a little bit complicated though. That's why I'm a little bit lazy about it. But I guess maybe that's fine. Yeah, okay, fine. So let's just say there's a find peak, right? And then now we have a left is equal to 0, right is equal to n minus 1 inclusive, I suppose. And then now, right? What do we do? So mid is equal to left plus right over 2. And then we want to see if mid is peak, then it is the smallest index where mid is greater than mid plus 1, right? Something like that, because it means that is the smallest index where this is sloping, right? So okay, so that means that if good of mid, and here we can say mid is going to be, so good is if this is sloping down. So if this slopes down, then we want to try a smaller number where mid is the right, is a possible number. So okay, this may have to be n minus 2, so that doesn't, because that checks mid plus 1. Okay, else plus 1, and then yeah, then we return left, right? And then we have to let's call it peak good, right? So def peak good of target, right? So we just return, let's call it a get function. Get mid is greater than get mid plus 1, right? Also get of some index is just return mountain array that get of index, right? Reason why we write it this way is because now we can add caching so that we don't make them make a call for the same number more than once. It probably doesn't matter, for especially when n gets bigger or doesn't come up as much, but it's a nice practice to kind of, you know, just at the very least for the smaller arrays, it should help a bit. So here we find peak, right? So yeah, peak is equal to find peak, and then I guess technically this cannot be 0, but that's fine. I don't care about that. And then now see if it is on the left side, right? On the left side of the mountain. Fine from left, maybe. Maybe we can generalize this a little bit better, but for now I'm a little bit lazy, so let's just keep it that way for now. Is going to peak. Peak will be going down after that, so peak. Yeah, I guess that's fine. Whatever, should be okay. Maybe we should pass in peak. I think that's a little bit better. Okay, right. Mid is equal left plus right, right? And then now if let's just say if get of mid, if this index is greater than if this is greater than target, is it? Yeah, this is greater than target. Then we want to go to the left side, right? Right is equal to mid minus 1 because we want to try a smaller number. Else, if get of mid is less than target, then we choose left is mid plus 1 because we have to get past mid, and then else we can return mid, right? And here we can return left just as the left is equal to right, and then yeah, and then left found maybe, or find left is equal to find from left the peak, and then if find left if let's do a get, if this index is equal to target, then we can return find left. Otherwise otherwise we do the same thing, but now the other direction on just so much code, and I don't even feel good about writing this code. There is some possible optimization here, but I don't know. Right, and this is just on the right side, or like not optimization, just in terms of writing code a little bit cleaner. But yeah, okay. Now this is decreasing now, right? So if this is greater than the target, then if this index is greater than the target, then you want to go to the right side. So then left is equal to mid plus 1. Else if get mid is right is equal to mid minus 1. Else we can return mid because they're the same. Maybe we could test it for that first. I don't know. Shouldn't matter. Then yeah, find right is equal to find from right or peak. If get of find right is equal to target, then return this index. Otherwise we return -1, or is it right? So let's give it a spin. Did I have a typo somewhere? Probably. Oh, here. Oh, whoops. Looks good here. Looks good here. I'm a little bit lazy to add more test cases. I'm gonna just give it some. Also, I'm really tired, to be honest. Like, I can't even keep my eyes open. It is midnight here in Taipei. Oh, I'm in Taipei, by the way. I don't know. See, I don't even know if I mentioned it already. So have it. Well, yeah, what's the complexity here, right? We do 3 binary searches. This is going to be log n. And yeah, we do okay. We don't, what did I do last? Wow, that was 4 years ago? Jeebus. I guess I mostly did the same idea, except for I named things maybe slightly better. Yeah, I don't really have much to add to this one. Hopefully this made sense. I probably, if I was on my home computer and less tired, I would draw this out a little bit. But yeah, we basically just find the peak, and then this just becomes the standard binary search on the left and on the right, and that's it. I am gonna pass out, so stay good, stay healthy, take good mental health. I'll see y'all later and take care. Bye bye.